You know, inside every single electronic device you own, your phone, your laptop, you name it, there's this constant hidden battle going on. And it's all about electricity. See, on one side, you've got all these super sensitive circuits that need a perfectly smooth, constant voltage to do their job. I mean, any little hiccup can cause chaos. But on the other side, the power we feed them, whether it's from a battery or the outlet in your wall, is, well, it's messy. It goes up and down, it has ripples, it's anything but stable. So you have these fragile circuits needing a steady hand, but they're getting power from a source that's all over the place.
So that's the big question, right? How in the world do engineers solve this problem? How do they take that shaky, unreliable power and make it perfectly smooth and stable for the electronics that depend on it?
Well, the answer comes from this tiny but incredibly brilliant little component. This is our hero for today, the Zener Diode. It's a device designed for one specific job, to bring order to that electrical chaos. Okay, so here's our game plan. First, we're going to figure out what exactly makes this diode so special. Then we'll dive into the physics behind its superpower, something called the breakdown principle. After that, we'll see how to actually visualize its behavior, understand its most critical job as a voltage regulator, and finally, I'll give you the perfect game plan to ace any exam question on this topic. All right, let's kick things off. To really get why this thing is so important, we have to start with the basics. What is a Zener diode, and what's its secret? Okay, so here's the official textbook definition you need to know. It's a type of PN junction diode, but here's the twist. Its magic has nothing to do with letting current flow forward. Its whole purpose, its entire reason for being, is built around this unique state called the reverse breakdown region. That's where it shines. So, to put it simply, and this is a huge point for any exam, think of it like a special kind of gate. Normal diodes are like a one-way street. The Zener diode, though, has a special rule. If you push electricity backward against it with enough force, a very specific voltage called the Zener voltage, it suddenly opens up and lets the current flow backward. So how does it get the special power? Well, it all comes down to how it's made. The secret ingredient is that a Zener diode is heavily doped. All that means is that they add a lot more impurities into the semiconductor material. Doing this creates a really, really thin depletion region. That's the little barrier inside, and it's this thinness that's the key. It allows the diode to break down at a very precise and very predictable voltage. Okay, so we know what it is and what it's made of, but now for the fun part. How does it actually work? Let's get into the physics of the breakdown principle. The science behind it has a name, and you're definitely going to want to remember this one. It's called Zener breakdown. This is the physical process that makes the whole thing possible. So let's walk through what happens step by step. As you start pushing that reverse voltage higher, the electric field inside that super thin depletion region gets incredibly strong. I mean, so strong, it literally starts yanking electrons right out of their atoms. This creates a sudden flood of current flowing backward, but here's the magic. Even with all this current rushing through, the voltage across the diode itself stays completely locked in place. It doesn't budge. And that right there, that's the whole point. All that complicated physics boils down to one simple, unbelievably useful fact. Once it hits that breakdown point, the voltage across the Zener diode is rock solid. It becomes a perfect constant voltage reference. Okay, talking about it is one thing, but engineers love to see the data. So how do we actually visualize this weird behavior? For that, we turn to something called a VI characteristics graph. It just shows us the relationship between voltage and current. So this graph basically has two parts. When you apply voltage in the forward direction, the Zener acts, well, just like a boring old diode. Nothing special to see here, which is why we don't really use it that way. But when you apply the voltage in reverse, that's where the story gets interesting. At first, almost nothing happens, just a tiny bit of current leaks through. It stays that way until you hit the Zener voltage, or VZ. See that sharp drop on the graph? It looks like a cliff. That's the breakdown point. And notice how the line becomes almost perfectly vertical? That's the visual proof. It shows that no matter how much the current changes from there, the voltage across the diode is locked solid at VZ. That's our constant voltage, right there on the graph. So we've looked at the construction, the physics, the graphs, but let's circle all the way back to the beginning. Why does any of this actually matter? How does this little component solve that big power problem we started with? It all comes down to its number one job, voltage regulation. The whole purpose of a Zener diode in a circuit is to take a messy, fluctuating voltage and create a perfectly stable, constant output voltage. If you remember one thing, remember that. It's the most common application, and it's a huge topic in electronics. And believe me, once you know what to look for, you'll realize these things are everywhere. They are the silent heroes inside power supplies, making sure your devices get the exact voltage they need. They're in protection circuits, acting like bodyguards for sensitive chips, shielding them from dangerous voltage spikes. They are absolutely fundamental. And why do engineers love them so much? Because it's an elegant solution. The circuits you build with them are super simple, the diodes themselves cost pennies, and they provide incredibly reliable control over voltage. It's the perfect engineering trifecta: effective, cheap, and simple. All right, let's bring it all together. If you're studying this for a class or an exam, you need a clear way to structure all this information. So here it is, your official game plan for acing any question about the Zener diode. Just follow this flow and you can't go wrong. Start with the simple definition. Then explain how it's built. Remember that heavy doping? From there, you explain the principle behind it. That's Zener breakdown. That leads right into explaining how it works. Then you show its behavior with the VI graph. And finally, you wrap it all up with its most important application, voltage regulation. Seriously, if you can walk through those 6 steps in order, you've proven you understand the topic completely. It turns something that seems complex into a series of clear, connected ideas that are really easy to remember and explain. It becomes an easy win. And there you have it, the Zener diode, a tiny component that solves a massive problem. It really makes you wonder, doesn't it? What other little, almost invisible pieces of technology are working hard right now to power the devices we use every single day?